Right. So welcome to week 9 of the NPTEL live discussion, which we are having on principles of signal estimation for OFDM MIMO wireless communications. And in the last week, we discussed the MMSE estimate, that is minimum mean squares estimate, where the parameter to be which we are estimating is also random in nature, right? So it has a prior distribution of its own. And we saw that the MMSE estimate is basically integration of the a posterior probability uh, with respect to h, or it is the expectation of h given y, right? So in this week, we will see how to compute the MMSE estimate with certain assumptions. So first we are going to see MMSE estimate derivation uh, for Gaussian parameter, right? When we have the that is when the parameter which has to be estimated is Gaussian distribution, is having Gaussian distribution. So the first assumption which we have is that our parameter and the observations are both Gaussian distributed and they are not independent to each other, right? So they are jointly distributed to each other. The next assumption which we have is that their individual expectations, that is expectation of h and expectation of y, is 0, right? So there is 0 mean, right? Okay. And let the expectation of h square, that is the second moment, is basically uh, denoted as RHH, and the second moment of the observation sample, that is y, is basically RYY, and it is sigma square h and sigma square y respectively. So first we will want to define something which is called correlation coefficient. So when two random variables, right? Two random variables, if they are dependent on each other or they are jointly distributed with each other, then there is some correlation between both those random variables, right? If they are independent to each other, then the correlation is 0. Okay? So the correlation is defined as expectation of hy divided by their standard deviation, sigma h times sigma y. Okay, and this correlation is strictly between -1 to 1. Okay, so if the correlation is -1, then that means that h and y are uh, negatively correlated to each other. Now, what is the meaning of negative correlation? So negative correlation means that if you have, say, h and y on the y-axis and x-axis, then negative correlation means that as y increases, then h decreases. Just a minute. Hello. Okay. Yeah. Sorry for the pause. Similarly, if rho is +1, that is if we have a completely positive correlation, then it basically means that as y increases, then h also increases, or if y decreases, then h decreases. So this is positive correlation. Negative correlation means if one parameter increases, then the other will decrease. Okay, and if rho is 0, then that means they are completely independent to each other. So it is very random. So we can't predict the shape of the curve. So there will be, it might be possible that as y increases, h decreases, or as y increases, for some instances h may also increase. So this cannot be predicted if h and y are independent to each other. So this happens. Sorry again. All right, so now we have a joint vector. Uh, is the screen visible? Okay, thanks. Yeah, so now we have the joint vector h and y. So h is my parameter, and y is my observation. So now we are going to define a covariance matrix. Okay, what is the covariance matrix? So covariance is, so we compute the covariance as shown in say step 1. So we compute the expectation of h and y, and we multiply it with h and y. So what you will see is that you have basically h square, hy, yh, and y square, right? So what is expectation of h square? It is basically sigma h square, because the mean is 0, right? Mu h is 0. Similarly, expectation of y square is sigma y square, right? Uh, Now, how will we compute expectation of hy? Okay, so if you just remember this, what we derived here. So rho is basically expectation of hy divided by sigma h times sigma y, right? Therefore, uh, expectation of h times y will be rho sigma h sigma y. Okay, so this is what we have. So 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 the non-diagonal elements will be rho times sigma h sigma y. Okay. So this is my covariance matrix. Okay. Now we need to find out the R inverse. So the question is, why are we finding out the covariance matrix? Why do we need to find out R inverse? So we'll come to that. We'll see the usage of R and R inverse. So how to find out R inverse? So it is basically 1 by determinant, and you do the standard cofactor method, and you will get R inverse. Okay, where determinant of R is sigma square h sigma square y 1 minus rho square. Okay. Now we want to calculate expectation of h given y, because h hat is basically expectation of h given y, right? So this is what we need to find out. So this is our aim. Okay, what we need to find out. So for that we need to find out the uh, conditional PDF, that is probability of h given y. Okay. So what is the conditional PDF? So this is my conditional PDF, right? So conditional PDF is basically joint PDF divided by the marginal PDF. Okay, this is the basic rules of probability. So so we need to first find out what is the joint PDF of h and y, assuming that h and y are jointly Gaussian distributed to each other. So we first see what is the denominator, that is the marginal probability of the observation. So it is straightforward, 1 by under root 2 pi sigma square y, expectation of minus y square over 2 sigma square y, right? So this is the marginal PDF of y. Now for the the numerator, which was the joint PDF of h and y. So this is a multivariate Gaussian PDF definition. So in that we have 1 by 2 pi sigma square. Instead of sigma square, we have the determinant of the covariance matrix, right? And inside the expectation we have hy times R inverse hy. So that is why we had to compute the inverse of the matrix and the determinant of the covariance matrix. So covariance is actually very important in multivariate uh, statistical analysis, right? And that too, especially when the random variables which we are considering are not independent to each other, right? So if we substitute the values of determinant R and R inverse, then we get this expression which has also been derived in the class. So finally, the probability, the conditional PDF, that is probability of H given Y, will be joint PDF divided by the marginal PDF. And now we will be dividing, both the PDFs which we derived earlier, and this is the final expression. So this is the probability of H given Y. Okay. So this is my conditional PDF probability. Now, in this expression, if we denote 1 minus rho square times sigma H square as say sigma tilde square, and similarly say rho times sigma H by sigma Y times Y as mu tilde, right? So this the conditional PDF is, if you see, this is looking very familiar to the Gaussian distribution, right? So this is my conditional PDF, right, of H given Y. And if and what will be the expectation of this H given Y? Then it will be mu tilde, right? It is straightforward. And what is mu tilde? It is rho sigma H over sigma Y times Y. And this is my MMSE estimate. So what is my MMSE estimate dependent on? So it is dependent on Y, which is my observation. It is dependent on sigma H, which is the standard deviation of the variance of the parameter which we had to estimate. It is dependent on sigma Y, which is the variance of the observation, and it is dependent on rho, which is the correlation between H and Y. Right. So okay. And note that this is the MMSE estimate when we assume that H and Y are Gaussian distributed, and they are not independent to each other. That is, they are dependent random variables. Okay. Also, the mean squared error is basically sigma tilde square, which is 1 minus rho square into sigma H square. So if you note here that if my rho is 0, right? If my rho is 0, say this is equation 1. So in equation 1, if you see if my rho is 0, then the mean square error is sigma H square, right? And if my rho is 1 or minus 1, then the MSE is 0. Like if my MSE is 0, that means there is no deviation of H hat from H, and so we are basically getting the best estimate when rho is plus 1 or minus 1. And if rho is 0, that is, if both are independent to each other, then we have the maximum error or variance between H hat and H. So what we observe that the independence condition, right, when rho is 0, that is when H and Y are independent to each other, in that case the error is maximum. Okay, in that case the error is maximum. Okay. So now we had seen initially that expectation of H square was sigma H square, which is also RHH. Expectation of Y square is sigma Y square, which is RYY, and expectation of HY is basically rho sigma H sigma Y, which is RHY. Okay. So what is H hat? So H hat we derived earlier, it was rho sigma H sigma Y. So if we multiply sigma Y in the numerator and denominator, then we see that we get RHY times Y divided by RYY, or we can also write it in this fashion, RHY RYY inverse Y. So this is my MMSE estimate. So we are just trying to simplify the expression. Okay. So basically, if you know the covariance matrix, right? If you know the covariance matrix, you have RHH, RHY, RHY, RYY, right? So you just need a covariance. You just need to plug in the covariances to compute the MMSE estimate. Okay. Similarly, the mean squared error will come out to be RHH minus RHY RYY inverse RYH. Now we'll take the case when we have a non-zero mean. So these are the two cases which I will be taking. There are many other cases, when so this is still the case where y is of the form y is h plus v. Okay, we are still playing with this. Okay. So there will be the channel estimation. So I'm not going to cover that because that has already been covered in the lecture. So I just want to explain to you the main basics behind MMSE estimation. So as we saw here, so you need to first compute the probabilities, right? You need to compute the PDF. So you need to find out the conditional PDF, that is probability of h given y, and for that you need to divide the joint PDF with the marginal PDF, and you need to first find out the joint PDF, and you need to divide it with the marginal PDF, and that is what you have, right? So that's the only thing which you need to do. So you need to understand how to write the PDFs, right? How to write the distribution in a multivariate Gaussian case. That is important, and you need to understand how the covariance matrix is made. Okay, so those who have joined late, I can see few people have come. Can after the class ends, you can see the recording. Okay, so for the non-zero mean case, so the first case which we considered was when the mean was 0, and for the non-zero mean case, say expectation of h is say some mu h, and expectation of y is say some mu y. Okay, now all right, so let h tilde, it be h minus mu h. So if I subtract the mean from h, so h minus mu h will basically be a zero mean Gaussian. Okay, similarly, y tilde is y minus mu y, then y tilde will be a zero mean Gaussian. Okay, now okay, so some basics behind the covariance and correlation. So the covariance matrix are, okay, it is defined as for this case, since we have two variables, right, h and y. So so this is covariance of h and h, covariance of hy, covariance of yh, covariance of yy. Okay, so this is how a covariance matrix is constructed. And in general, covariance for between any two random variables x and y. So expectation of x minus expectation of x times y minus expectation of y. Okay, so here if you see there is an expectation, and so it is kind of expectation inside expectation. Okay, so you are taking x minus mu x times y minus mu y. Okay, and you are taking an expectation of all that. So this is the definition of covariance between any two random variables. Okay, so if I solve this, so this will be xy minus x times expectation of y minus y times expectation of x, and plus expectation of x, expectation of y. Right. Now, if we take the outer expectation inside, so you will see that we get expectation of xy, which is the first term. For the second term, if you see, so expectation of y is a constant. Okay, expectation of y is already a constant because all the randomness has been averaged out uh, already. Right? So expectation of y is basically what will be expectation of y. So this is expectation of y itself. Okay. Similarly, expectation of x is expectation of x itself, because expectation of x and expectation of y are already a constant. So the second term will be expectation of x times expectation of y. Similarly, the third term will be minus expectation of y into expectation of x. And finally, we have the fourth term, that is expectation of x times expectation of y, which will be expectation of x, expectation of y. Okay, right. And if you further solve this, you will finally get this expression, that is covariance of x and y is expectation of xy minus expectation of x, expectation of y. So this is the final definition of covariance between any two random variables. So expectation of xy minus expectation of x times expectation of y. Now, if x and y are independent, okay, what if x and y are independent? So in that case, what happens? So you know the definition of independence. So the expectation of x times y is expectation of x into expectation of y. So in that case, the covariance becomes 0. Okay, so both the terms cancel out each other. And the correlation coefficient is defined as covariance of xy divided by the root of variance of x times variance of y. Okay, so this is just to if you have some uh, just to brushen up the mathematics. Okay. So now in this case, when we have a non-zero mean, right? The non-zero mean is there. So what will be r h tilde h tilde? So now if you see what will be my r covariance matrix, so it will be r um, r h tilde h tilde, r h tilde y, r y h, and r y y. Okay, so if mean gets added, does my variance change? Okay, that is the question. So let's see. So what will be r h tilde h tilde, where h tilde is h minus mu h. Okay. So the as we defined covariance above, so it will be expectation of h minus mu h times h minus mu h. So it will be h minus mu h squared. So if you open it, so you have h square plus mu h square minus 2h mu h. And here if you see what is expectation of h square, so you have sigma square h, right, plus mu h square. Okay, so this is the first term. Okay, the first term expectation of h square is sigma square h plus mu h square. So how does this come out? So if you just see in the black what we have written, so the variance is the second moment minus first moment squared. Right, this is the definition of variance. So sigma h square will be expectation of h square minus mu h square. Therefore, expectation of h square will be sigma square h plus mu h square. Right. So this is my first term, expectation of h square. So if you solve this, what we see is that even after adding mean to h, my covariance of h tilde times h tilde does not change. Right, so this is a very important property. So if you are adding mean, so if you just take the the scalar case, say you have a x is a Gaussian, say a comma sigma square, where a is my mean. So if I have some x tilde at say x plus b, right? So this will be Gaussian a plus b comma sigma square. So my variance part is not changing, right? So it is just like my mean is shifting, right? So say earlier our Gaussian was centered around a. Now it is just being centered around some a plus b. Right? So this is what is happening. So if my mean is getting added or subtracted, then the variance is not changing. Like this is very important property which you should note. Similarly, we can prove for all other cases. R y tilde is also r y y. Similarly, r h tilde y tilde is r h y. So what we see is that my r dash is basically r itself. So my covariance matrix does not change on adding mean. This is the main point you should remember. And in the previous case, we had derived that our h hat is rhy ryy inverse times y. So now what will happen? H hat tilde will be, everything will be everything has been modified. Uh, and what is h hat tilde? It is h hat minus mu h, which was our definition. and all the covariances are the previous covariances only, right? And so finally what we get is that you have y minus mu y, which replaces y tilde, and you have a plus mu h. Okay, so this is the MMSE estimate of Gaussian parameter with non-zero mean. Okay. So earlier we saw the case for zero mean, and now this is for non-zero mean. Okay. And I'll just discuss this because it will be useful in the numericals which we'll be discussing right now. So if we have a modified signal model, say yk is h times xk plus vk, where h is my fading channel, and we have discussed this in the maximum uh, log likelihood estimate, when we derived it. So I'm just writing the basic formula. Okay, so the derivation has been done in the lectures. So it is the this is given as in say equation 1, and just remember this, that x transpose y divided by x transpose x, this was the maximum likelihood estimate of h. Okay, you need to recollect back of the previous weeks, and the variance of the maximum likelihood estimate was sigma square over x transpose x. Okay, so h hat MMSE is nothing but the MLE, right? MLE divided by variance of MLE plus prior mean divided by the prior variance divided by 1 by the variance plus 1 by prior variance. So if you see, this is the expression, right? So this is my MLE estimate, right? This is my prior mean, and these are the variances, right? Which we are. So it is it is a weighted average. The MMSE estimate is a weighted average. So you are averaging out the MLE and the prior mean such that the weights are the inverse of the variance. So this is very important to understand. So what is the MMSE estimate? So it is nothing but the MLE estimate plus the mu h, which is your prior mean, right? The mean of the parameter, and you are dividing or you are multiplying with 1 by the variances, right? The variance of MLE and the prior variance, and it is kind of an averaging, which you are doing. Okay, so any doubts and then we'll go to the numerical solving. Any doubt? No doubts. Okay. So, in week 9, start. Okay, so we are given that we have jointly Gaussian random variables, okay, h and y, with mean 0 each. Okay, so initially we are given the 0 mean case. Okay, and they have variances sigma square h and sigma square y. Let rho denote the correlation coefficient, the joint PDF of h and y. Okay, so what is a joint PDF? So as given in lectures and as we just discussed also, so the joint PDF of h and y is 1 by under root 2 pi square 1 minus rho square sigma square y sigma square h multiplied with exponential minus sigma y square h square minus 2 rho sigma h sigma y h y plus sigma h square y square divided by 2 times 1 minus rho square sigma y square sigma h square. Okay. So this is what we have. This is the joint PDF, right? You can just check. So this is option B. This is option B. Any doubt in this? Yeah, someone wants to say something? Feel free. No? Okay, so we'll move ahead. So, right, question 2. So let us consider a slightly modified version of sensor network. And this is a yk is, so this is yk is k times h plus vk. And the noise samples are, IID Gaussian, mean 0, variance sigma square. So what is given is that V is Gaussian, IID mean 0 and variance sigma square, and each parameter H, and what is given is H is Gaussian, mean 0, variance sigma H square, and he has asked what is MMSE estimate of H hat. So in the class, in the lectures, it is done as X times H plus V. Okay, so this is the same thing. Okay, just the variable has been replaced with K, so we should not get confused, right? And note that the K is from 1 to N. Okay, so what is my H hat, right? So as done in the lectures, it is X transpose Y divided by sigma square plus mu H over sigma H square divided by X transpose X divided by sigma square plus 1 by sigma H square. Anyone is having any doubt in this? All right, so what will happen? So what is X transpose Y? Okay, what is X transpose Y? So X transpose Y is yeah, so my X, what is X? So X is basically, if you see, X is basically K's, right? So it is 1, 2, N. Okay, and this is my K. Right. So X transpose Y is basically summation. K is 1 to N, K times YK. Right. What is my sigma square? Sigma square is sigma square. Mu H is 0. Sigma H square is sigma H square divided by X transpose X. What is X transpose X? So basically you are multiplying vector K with vector K. Right. So what will you have? K is 1 to N K square divided by sigma square, right? And this is also plus 1 by sigma H square. And if I just solve it here, so just note this, right? So you have this uh, progression series, right? So you should remember. So how is this solved? So this is summation K times YK over sigma square divided by, now the first term is basically N plus 1, 2N plus 1 divided by 6 sigma square plus 1 by sigma H square. Okay. So this is my final answer, which is option D. Okay. Any doubts? Any doubt? No doubt? Okay. So we move ahead. So this question is similar to the previous question. And what he has asked is what is the mean square error of the H hat MMSE, which we derived. So what is the MSE of H hat? So this has been done in class. So this is 1 by X transpose X over sigma square plus 1 by sigma H square, right? And so we just need to solve this. So this is 1 over, what is X transpose X? This is again K square over sigma square plus 1 by sigma H square. And what is summation K square? So as we saw, it is a progression series. So this is N plus 1 to N plus 1 over 6 sigma square plus 1 over sigma h square. So this is option A. Any doubts to anyone? No? Question 4. So it's still the previous two question. Okay. What is the posterior distribution of the parameter h? Okay, so this is what they have asked. So since here our the noise samples are Gaussian, the parameter is also Gaussian. That is why the posterior distribution of h, right? That is probability h given y, right? So this what it will be is it will also be Gaussian with some mean and some variance, right? And since Gaussian is not given here, so it is none of the above. Right? So the answer is Gaussian distribution. Okay. Next question. So again the same signal model. What is the maximum likelihood estimate of the parameter h? So see what has been asked in the question. Right? So they have asked what is the maximum likelihood estimate. Okay, MLE. MLE. So what is the maximum likelihood estimate? So the maximum likelihood h hat MLE is x transpose y over x transpose x. That's it. So what will be x transpose y? So this will be summation k times yk divided by summation k square, and this will be summation k times yk divided by n plus 1 2n plus 1 by 6. So this is what we have. So this is option B. Any doubts? No doubt. Okay. So question 6. Right. So now we are given a fading channel estimation problem. So h times x plus x plus v. And we have some x vector. We have some y vector. Okay. Vk is IID Gaussian. H is Gaussian with mean mu h variance sigma h square. So and the covariance matrix is V vector. Right. So what they have asked. So you should remember as it was done in class that expectation V transpose. Right. And what is VV transpose? So here the noise information. Yeah, so the noise is given to be IID if you see in the question, right? So we have IID Gaussian noise. So basically what we have is that expectation of V1 square, V1, V2, so on, V2, V1, V2 square, and this will go up to Vn square. So this is expectation of okay, let me take the expectation inside. So we'll be basically left with sigma square and on the diagonals and 0 on the non-diagonals. So this is basically the expectation of VB transpose. So this is option B. So this is sigma square times I. Any confusion? Question 7. So again, the fading channel problem. We have some X given, we have some Y given. And what is the LMMSE of H hat? Right. So if you remember, H hat is basically X transpose Y over sigma square plus mu H over sigma H square. This is divided by norm of X square sigma square plus 1 by sigma H square. So this is what has been done in class and in lectures. Okay. So this is option D. Straightforward question. Question 8. So now we are given, a vector x 2, 3 by 2, minus 1 by 2, 1 transpose. We are given vector y 1, minus 3 by 2, 2, 1 by 2 transpose. Okay, we are given x and y. We are given sigma square is 6 dB. So if you convert it in watts, this will be 2 to the power 6 by 10. This is approximately 4. Oh, sorry, it is not 2 to the power, it is 10 to the power. And so this is sigma square is this, and we are given mu h is 2 and sigma h square is 1. Okay, so he has basically asked what is h hat. Okay, what is h hat? So we just need to, use this expression. Okay, we need to compute all the values and put it in this expression. So let's do that. So, okay. So what is x transpose y? So you have 2, 3 by 2, minus 1 by 2, 1. Just multiplied with 1, minus 3 by 2, 2, 1 by 2. So you can also do with me. So this will be 2 minus 9 by 4, minus 1 plus half. And this comes out to be minus 5 by 4. And x transpose x. This comes out to be basically 2 square plus 3 square by 2 square plus 1 square by 2 square plus 1 square. So this is 30 by 4. And if we basically we need to just plug in the formula, right? So x transpose y over sigma square plus mu h by sigma h square divided by x transpose x by sigma square plus 1 by sigma h square. And if you just plug in everything in this, you get the answer as 29 by 46, which is B. So you just need to plug in these values in this. Okay, so all the values are shown here. Any doubts? Okay. Question 9. So same question. They have asked what is the MSE of the MMSE estimate. Okay, so what is the MSE? So MSE is basically 1 over x transpose x by sigma square plus 1 by sigma h square. Okay, straightforward. And x transpose x is basically 2 squares plus 9 by 4 plus 1 by 4 plus 1. And this comes out to be 16 plus 9 plus 1 plus 4 by 4. This is 30 by 4. Okay, this is 15 by 2. So it is x transpose x. So you just need to just plug in the values here. 15 by 2 divided by sigma square, which is 4 plus 1 by 1. Okay, and this will come out to be 8 by 23. Any doubts? Okay. Final question. So again, the same signal model which we have been using for the past 2-3 questions. And the probability that the estimate h hat lies within a radius of 1/4. Okay, so if you remember in the previous question, we computed the MSE of h hat, which came out to be 8/23, right? See this question. So okay, this is MSE of h hat. So h hat minus h will be Gaussian distributed with mean 0 because we are doing h hat minus h. Okay, and the MSE is 8/23. So what we need to do is probability of -4 h hat minus h 1/4, right? So this is what we have to remember the week 1, week 2 questions. It used to be in this fashion. So we need to divide it by the standard deviation to make it a unit Gaussian, right? So we need to make this into a unit Gaussian. Okay, what unit Gaussian? That is 0, 1. So we will divide it with root of 8/23 h hat minus h divided by root of 8/23 1/4 divided by root 8/23, right? And what is this? So this is probability of root 23/8√2. This is my new random variable. This is 23/8√2, and this will be 1 minus 2q 23/8. So this is B. Any doubts? Any doubts? Any other thing you may want to discuss, feel free. If nothing, then that's all. Oh, okay, so I'll stop sharing.
Thank you, sir.
Okay, thanks. You all can leave. Thanks.